Okay, now that we've learned the universal wave equation, v equals f lambda, from our previous activity where we derived the equation, we're going to be able to use this now to solve some basic problems involving waves. So those be basic problems, but we'll include some sketches just to help out with the understanding as well. Okay, so let's say that we have a wave that has an amplitude of 25 centimeters. Great. It has a frequency of 45 cycles per second, and you can see from the lesson sheet I left a little bit of space here just to fill this in. The reason being is that when we talk about frequency, when you're in the learning stages, it's often tough to see that it's 45 cycles happened every second. So imagine snapping your fingers or waving your hand and doing that 45 times in 1 second. That would be the equivalent. So another way of writing this is 45 hertz, that's the same thing, or 45 inverse seconds is the same thing, or 45 seconds to the minus 1. These are all equivalent. 45 cycles per second, 45 hertz, 45 1 over seconds, or 45 per second, I guess, and 45 inverse seconds is how you could say that. So these are all the same thing. Don't get confused and think like, wow, what's his inverse second thing? Well, it's just hertz. Or what's his 1 over seconds thing? Oh, it's inverse seconds. Or it's hertz. Or it's cycles per second. A lot of times, like just understanding that it's cycles per second is more helpful than ever writing these things out here. So now that we know the frequency and the wavelength, or the amplitude, sorry, that's the amplitude, and a distance from crest to crest is 23 centimeters. It says calculate the speed of the wave and include a sketch. So, you should get practice drawing these sort of sinusoidal waves, just for one, because they're fun, and two, because they're handy, especially when we start talking about standing waves and things like that. So here's a wave here. It's got a little bit of a glitch. That's okay. Now, it says from crest to crest. So that's the same thing as trough to trough, but understanding what the wording is asking, and what it's saying, sorry, is pretty important. So this is the wavelength here, measured from there to there, and it's equal to 23 centimeters. The amplitude, although we know the speed of the wave is not dependent on the amplitude, is 25 centimeters, like so. And it asks us to calculate the speed of the wave. So how fast is this wave moving? We'll just we'll assume it's going that way, just to make it easy. We know the wavelength is 23 centimeters. We know the frequency is not 20, it's 45 hertz. And we're trying to find out the speed. Well, this is a simple problem. We don't even have to rearrange the formula. So we'll start out easy. V equals f lambda. We've got 45 times 23 is going to give us 1,035 centimeters per second is our speed. Or if you were inclined to convert the 23 centimeters into meters and make it 0.23 meters, we would see this would be 10-ish meters per second. I just rounded it, 10.4 meters per second. So that's it. That's a simple type problem. Didn't have to rearrange anything. Really just wanted to use it to really hash out the idea of what the units for frequency are, to show you that sometimes the amplitude will get thrown in there, although it's not necessary, and that you just need to use your governing equation of V equals f lambda. Okay, let's move on to another problem. And again, you can download the problem from the description below. A wave has a frequency of 20,000 hertz, 20 kilohertz, and a distance from one crest to the adjacent trough of 0.0134 centimeters. Calculate the speed of the wave. Make a sketch. Okay, well, let's start with making the sketch. Okay, I can probably stop at this point because I have more information than I need. And in here it says that we know the frequency is 20 kilohertz, which is 20,000 hertz. We're trying to figure out the speed of the wave. like so. We know the wavelength is from, in this case, we'll just do it from crest to crest. So there's our wavelength from crest to crest. But it tells us that the distance from one crest, so let's just say from here, from this point, to the adjacent, the word adjacent just means beside, trough, this distance here is measured to be 0.0134 centimeters, or that many meters. Okay, so why would this information be given to us? This information is given to us because the wavelength is clearly not this distance. The wavelength is from crest to crest, and since we know from crest to trough is this much, we know that double that is the actual length of the wavelength. So really it's 2 times 0.000134 meters, which is 0.000268 meters. We probably could use scientific notation here to make this easier than putting all these zeros, but at this point we'll just continue. V equals F lambda. The frequency was 20,000. The wavelength 0.000268, like so. Gives us a speed of 5.4 meters per second when you multiply those out. If I had left this in centimeters per second, I would have ended up with 0.054 centimeters per second, which is also fine. The units don't matter in that case. It depends on what you're looking to solve for. Okay, so that again, the first one was very basic, V equals F lambda. The second one threw a little bit in there with this crest to adjacent trough information to figure out that we needed to actually calculate the wavelength by multiplying by this factor of 2, because that was only half of the real distance for the wavelength. So let's move on to the third one in our series of just basic examples of this. Okay, so in this case we have a student that measures the distance from one crest on a water wave to another crest that has 2 troughs in between, and the distance is 30 meters that he measures. He times that this series of 20 crests passes 1 point in 4 seconds. Calculate the frequency and period of the wave and the speed at which the wave is traveling. Okay, slightly more complicated, a little more in this one than the previous ones. So what I'll do here is I'm going to just make the sketch again. And I need to draw a little bit more here because it starts talking about a crest and then 2 troughs, and so I'll need to make sure that I have at least 2 troughs depicted in this image. I'll go a little further maybe than needed, like so. Okay. Now we know that one wavelength is still, that doesn't change anything, it's still from here to here, 1 cycle. That's the time it takes to do that one pass, is the period, the distance, the horizontal distance measured from crest to crest is the wavelength. We talked about this. Now what we're going to look at, we're going to see here, is that it says the distance is 30 meters if we start at one crest. So let's say we start at this point here, and it says there's 1 trough, 2 troughs, and it says that the distance from one crest on the water wave to another crest, where there's 2 troughs in between, so that's to here, right there. So what we're looking to find at this point is we know that this is 30 meters as given in the question. Now the question becomes, how many wavelengths are there? Well, 1 crest, 2 crests, that's 1 cycle, 2 cycles. So 2 cycles have gone by. Well, in 2 cycles, we know there would be 2 wavelengths. So 2 cycles would be 2 wavelengths. So we know that really this 30 meters is 2 wavelengths. So 2 wavelengths is 30 meters. Well, if that's 30 and there's 2 of them, we know that one of the wavelengths is 15. So to mathematically write this, we would use what we have up here from our diagram and say 2 lambda equals 30 meters, lambda equals 15 meters. Again, you could just see it. It's easy, 15, 15 to get that. But when you read it, it's a little bit trickier. All right, let's calculate the period. We say, or the frequency, whichever one. It's up to, let's start with the frequency. So frequency is the number of cycles per unit of time. All right, well, it says that 20 crests go by 1 point in 4 seconds. So from crest to a crest is called a cycle. Right? Crest to a crest is a cycle. So if you're at this point, let's say, and a crest comes by, that's 1 cycle. So it tells us that 20 crests go by in 4 seconds. And since crest to crest is a cycle, we know it's 20 cycles over 4 seconds, which tells us that the frequency of the waves is 5 hertz. The period is the time interval, number of cycles. Okay. Well, it took 4 seconds to do 20 cycles, which is 0.2 seconds. And we know that these two are reciprocals. So we've got our answers. So if you want to do a little check, just since this is for your notes, frequency is 1 over the period. And since we calculated the period to be 0.2, 1 divided by 0.2 is 5 hertz. That worked. Well, if I have the period and it's 1 over the frequency, 1 over 5 is 0.2 seconds. So it checks out. If you were given one, you could easily calculate the other one by doing the reciprocal or taking the inverse. All right, well, let's find the speed of the waves different ways. Okay, so at this point we're just going to calculate the speed of the wave. We'll use 2 different equations. We'll do the first one, v equals f lambda. Well, the frequency was 5, the wavelength was 15, 75 meters per second. It's pretty quick, actually. Or another version of this is v equals lambda over t, since f equals 1 over t. So since frequency is 1 divided by t, I'm just replacing the frequency with 1 over t, and you get this equation right here. So that's 15 divided by 0.2, and you get a speed of 75 meters per second. Same answer. Now, these problems are going to get a little trickier. You could be given the speed of the wave, you could be given the frequency and asked to find out the wavelength, and then maybe from a sketch figure out how far it is from like a trough to the adjacent trough, or to 2 troughs further down. So there's different variations on this. You could be given the distance from a crest to the second trough. So then there would be 1 wavelength and a half a wavelength. So there'd be 3 halves of a wavelength in there. So there's different variations on how you can do this, but as long as you're okay with fractions, it shouldn't be a problem at all. Okay, thank you.